Thanks for coming to Science Sunday on such a cold day. It's nice to see. We've got a couple of young scientists. I always like to point them out. There's a young scientist in the back there. What's your name?
Amelia.
Amelia? Great. You interested in science?
Yeah.
Nice, good. I think you'll hear some interesting stuff today. And over in Dima, your son's name is?
Sasha.
Sasha? Okay, great. Welcome. And you like science a lot?
Yeah.
All right, good. So we hope to keep the young scientists coming in here and hearing interesting stuff. And it may not all be completely understandable, but that's not because you're young. That's because science has some challenging parts to it. But it's always good to look and think about it. So other than that, welcome you to come and join the service that's going on next. There's going to be a Buddhist talk. If you're interested in Buddhist thought, Reverend Mike Walker is going to have some talk about that. He had a really interesting talk last week about the letter from a Birmingham jail from Dr. Martin Luther King. So I think there's valuable stuff going on at the other end of the building too. So welcome, and with no further ado, we'll bring up another science lover.
Morning, Scott.
Good morning, science lovers. How fortunate I am to be a part of a community that loves this stuff. I've been in love with science since before I went to college, and I continue to be. You know, sometimes you go and you study something and, what's that good for? I've never had a job in science, but I still have maintained my passion about it. And it's so nice to be a part of a community that also appreciates some of the wonders of the universe and likes to take a scientific perspective. It wasn't always true that, whoops, come on.
Point it up at the...
Point it up.
You're not plugged in here.
Oh,
You got it.
oh, the little, yeah, okay.
It's science.
Yeah.
Technology great.
Yeah. I are a science lover, not engineer. Yeah, good. All right, let's see if this works. Okay. All right. So let me get my notes for today. All right. You know, there are big questions. You know, like I said, it's nice that I've been interested in science and a scientific explanation for the way the world works, the way the world has come to be. And that's part of what I would consider the big questions. You know, you can read them as well as I can, but, you know, how did we get here? Where do we come from? Where does all this other stuff come from? How long has the universe been the way it is today? All of these questions, and one of the interesting things about these kinds of questions is that they seem to be human-centric, right? How did we get here? What is our purpose? You know, what am I doing on this planet? When we tend to ask those questions, we tend to ask them from a subjective point of view. And there's been an assumption throughout most of human history, when we look around at nature and we see the differences between what human beings are capable of and our various competencies, we see a difference with other things in nature. Rocks don't communicate. Some animals communicate in a way that's more rudimentary compared to humans. It's reasonable to think that there's something special about humans, and I don't deny that. There is indeed something special about humans. But, you know, this year, Mike had the idea earlier, he and I were talking about discussing our origin story. And if you want to talk about our origin, you have to go back in time and really uncover a lot of science. So that's what we're trying to do. That's what I'm trying to do with this series of talks. And last time, past two times, we talked about the Big Bang. How did it all get started? Where did it all come from? How has the universe changed since the moment of the, or at least in the first moments of the Big Bang? And to answer some of these questions, historically, people have come up with all kinds of creation myths. And the mythology can range from the supernatural, or what I call magical, to the non-magical, or scientific. And the scientific methods that we use today are generally new in the course of human history. So previously, when people were addressing these kinds of stories and they needed to come up with some kind of explanation, some kind of story, I mean, we can't just suddenly be here. There has to be an origin story. Well, typically, people's origin stories entail the magical. But as we have discovered in the past couple of hundred years, we can do a good job of making stories about our origins that are based solely on the machinations of the physical world. How does the world work? What happens? What does it do? What does it lead to? Another variation on creation myths is cyclic versus one-shot. I think the Aztecs and the Indians, the people on the subcontinent, have this creation myth that entails a notion that the universe starts and goes along for a while and then restarts. So you could have a cyclic universe. There are other ideas where the universe had an origin and it keeps going. Right, from that, kind of like in geometry, you have the idea of a ray, something with a start point and no end point. You could have a universe that's always been around. Greek philosophy, some aspects of Greek philosophy, some other philosophies presume that the universe is the way it is and has always been the way it is. So there are different ways to approach this idea of what the universe is like, how things came to be. And it isn't a priori necessary to presume, other than the magical, non-magical delineation, some of these other ways that the universe could be are difficult to sort out. So we have found that the Big Bang happened, and the universe is expanding. If you run the reel backwards in time, metaphorically speaking, and in terms of our physical understanding of space and time and matter and energy, then the universe had an origin time. And we talked about that last time. I'm not going to recapitulate that. But you start looking at some of the origin stories. This is a popular one from Western culture, the Christian, Judeo-Christian origin story. You know, it's got things happening in a certain sequence. That's good. Right? Not everything could happen all at once. That's a good realization. But the ordering of things happening in this story is not quite what the evidence of nature has told us is the way things really occurred. This fellow came along, had a big impact on Christian theology. This is Aristotle, or a stone replica of Aristotle. And some of you know from my past discussions at Science Sunday that I have kind of a love-hate relationship with Aristotle. You know, he came up with a lot of the really important ideas in natural science and philosophy that have continued to be relevant for 2,500 years. On the other hand, he had some really strange ideas. You know, early in his life, he was an experimentalist. He lived on the island of Sappho, I think it was, and there was this tidal basin there on Sappho, and he would go out and he'd look at starfish and other fish that were in this basin and make some extrapolations that were almost hitting on the idea of natural selection, that the environment and the organisms had a feedback, and the organisms would have, he didn't know about the term, but what we would say evolved to be compatible with their habitats and whatnot. But then in his later life, he got away from this experimental idea of going out and seeing what nature has to tell us. And he just started coming up with these wild ideas, like women have fewer teeth than men. I don't know, you could count. He didn't. But Aristotle and his ideas and the ideas of geometers and other Greek and classical thinkers led to this notion of some creative force or creative agent being a great geometer. And you know, William Blake made this this painting. I think it's called Ancient of Days. And the idea is that the universe was designed. Right? All of this has a purpose and some higher design behind it all. And one of the things that thinkers throughout history, up until recently, have tried to do is figure out the mystical aspects of this design. And a popular approach to figuring out these mystical aspects is with something called alchemy. And this is a depiction of an alchemist. And here's some alchemical symbols, right? We've got symbols for, salt and air and earth, fire, and water, and all these things. And I think Aristotle and some others came up with this idea of the basic elements of the universe. And some of them think that the different elements had different shapes, and so water elements were round and soft, and fire elements were prickly and had jagged edges and whatnot. And you combine these physical characteristics in different ways, and you get the elements of nature. And alchemists tried to figure out these elements of nature, and one of the things that they discovered, or dreamed up, I should say, was they recognized that there were 7 celestial bodies that seemed to be magical, or maybe not, if not magical, at least quite different than other celestial objects. Right? You can see the stars. The stars generally wheel about the earth and change a little from season to season. But then there are these other things in the sky that are very prominent and brilliant and unmistakable, and they don't move with the stars. Things like the sun and the moon and the planets. And if you add up the sun, the moon, Mercury, Venus, Mars, Saturn, and Jupiter, the celestial objects, the distinct celestial objects that were known by the ancients, you come up with the number 7. Well, in Hebrew and Christian mythology, the number 7 is the perfect number. It's the number of God, right? The universe was created in 7 days. So this traces all the way back to Babylonian ideas. So why do we still have a 7-day week, right? It's an echo of this notion that 7 is a perfect and holy number. So numerology and alchemy got combined in this big construct to try and explain the universe. The Greeks decided that there were 7 wonders of the ancient world, not 6, not 8, 5, 7 shall be the number. And that's because the Greeks thought that 7 was a perfect number, right? We've got the 7 seas. If you try to count the oceans of the earth, it's hard to come up with 7. But everybody says sail the 7 seas. It's the North Atlantic, the South Atlantic, North Pacific, South Pacific, etc., right? Well, 7 is supposed to be the number of perfection. So some of these ideas got embedded deeply in our culture. And one of the things that science did was it went out and said, well, what is true about these? And then they found 9 planets and took one away, and now we end up with 8. And nobody went out and adjusted the length of the week for some reason. Now, 7-pointed stars, you see this in alchemical texts. And one of the goals of alchemy was to find something called the Philosopher's Stone. So there's a wonderful little story about this. I'm probably not going to get through all my slides today, and that'll be all right because I'm here. I live in the area. I'll come back. But here's an interesting thing about the Philosopher's Stone. The notion of the Philosopher's Stone that everybody likely has heard is the Philosopher's Stone will allow you to do elemental transmutation, right? You can take something like lead, which is almost as heavy as gold, but not quite, and sulfur, which is yellow like gold, but not quite gold, or mercury, which is shiny like gold and fluid, and maybe you can combine mercury and sulfur and lead in some special way and make gold. I mean, the only thing that lead seems to be missing is a yellow sheen, right? So you can add sulfur to it. Right? This was part of the idea, and with the Philosopher's Stone, the idea was that you could bring some base elements like lead and sulfur in the presence of this Philosopher's Stone, and it would become gold, right? And some people have the notion that that was the end goal of alchemists, and it was the end goal of some alchemists, and the state, various states, in Germany and the German states and whatnot, they didn't like this notion, and Christianity in general kind of frowned on the notion of alchemists. It was kind of witchy, a little witchcrafty, a a little too much for them to handle, so they went about the world and they found alchemists and they killed them. So, you know, this is a nascent science of the way that elements combine, and the way that one thing can turn into another. And sometimes alchemists would be hanged from a gilded scaffold, right? Because one of the things you know if you learn a little about economics is if you flood the market with some commodity that's otherwise scarce, you can change the whole monetary and economic system. Well, if your monetary system is based on gold and or silver, and you flood the market with gold and you make some in your laboratory, well, then that's a threat to society and the king, right? So this is all entailed in this notion that alchemy was a dangerous practice. So alchemists used to communicate with each other in this in special codes that they would use, and they would make up, you know, like the cereal box decoders from back in the day, you know, the secret codes for alchemy. And if I'm remembering correctly, one of the more infamous alchemists was Al-Jabar, and his code. A lot of people attributed these undecipherable texts to the work of Al-Jabar, and it became gibberish. So that's where the term gibberish comes from, is alchemy. Algebra was from somebody else. So I thought that Al-Jabar was algebra too for a long time, no, it's actually from another, an Arabic named fellow, but it wasn't related to alchemy specifically. So that's it was a mathematician. So, in any case, that's what a lot of people know about the Philosopher's Stone. But here's something a lot of people don't know about the Philosopher's Stone. The whole idea of getting to the element gold was because gold represented the sun, and the sun was perfect. The sun was eternal. The sun was a giver of life. So if you could find a mechanism to convert something else into gold, you could make that something else into a perfect, eternal element. And that was something that they could do with human beings, hypothetically. They could take the alchemist's stone and they could rub it on somebody or who knows what, and they could turn it into an elixir. Sometimes there's ideas that it could be liquefied and whatnot, kind of like mercury is a metal that's liquid. And if a human being somehow came into contact with this philosopher's stone, the idea that the human being would become perfect and live forever. That was one of the goals of the Philosopher's Stone, was to invent a pathway for immortality. So all of these notions, all of these human aspirations to understand the world, to understand how one thing becomes another, to search for perfection, to extend life, all of these things got conflated into this mystical practice of alchemy. But this guy came along, Isaac Newton. This is an incorrect depiction of Newton because he was left-handed. But this is from the latest Neil deGrasse Tyson version of Cosmos. And this is, Newton came along and standing upon the shoulders of some giants like Copernicus and Tycho Brahe and especially Galileo, he decided, or he discovered, I should say, that one could use mathematics and geometry to depict the machinations of the heavens, the orbits of the planets, not just the orbits of the planets, but explanations about why apples fell and hit scientists on the head, or how the tides worked, how the tides were related to the orbits of the moon and the sun. So this was pretty much the first person in history to discover that the laws of nature represented patterns. And the language of pattern is mathematics, right? So if you have something that happens regularly, cyclically, right, you can describe a mathematical function that represents that cycle, that tells you how long the cycle lasts, how high and how low the particular quantity goes. So Isaac Newton was among the first. Galileo did some as well, so did Kepler, but he was among the first and certainly the most prominent scientist back in the 17th century, the mid to late 1600s, who decided that mathematics was a good way to represent nature. In fact, Galileo, who I think Newton was born the year Galileo died, if I remember correctly, 1726, something like that. Anyway, Galileo had famously said that the book of nature is written in the language of mathematics, right? And that's something that we have continued to discover and validate for centuries hence. So one of the things that they discovered early on was that the universe was expanding. This was about the time that Albert Einstein, the guy with the weird hair, came up with his idea of relativity. And I'm not going to go into much depth about that, except to say that about the time that Einstein was active in the scientific world, there were a lot of discoveries about astronomy and astrophysics and cosmology, the way the universe is shaped, the way it evolves, the way it moves through time and space. And one of those discoveries was that the universe expands, as I alluded to a moment ago. And that implies that it had a beginning. Well, some scientists were trying to figure out, given the context of an expanding rather than an eternal and unchanging universe, how do we come up with particular events or processes that give rise to the chemical elements? Nothing magical or mystical about it. No philosopher's stone is sitting out in heaven transmuting hydrogen into praseodymium or anything like that. So how did the elements come into being? Well, the fellow who's pictured there with Albert Einstein is Sir Arthur Eddington. And some of you may remember Eddington for the famous experiment in 1919 where he validated that the path of a beam of starlight skimming across the edge of the sun is deflected by the gravity of the sun. And he discovered that during a solar eclipse, and it had been predicted by Einstein. And so as soon as that discovery was made public, Einstein became the most famous scientist in the world, and likely the most famous scientist in history, is because of the sun-grazing light beam that Arthur Eddington discovered. But Arthur Eddington was very interested in other things too. One of the things he was interested in was stars. He was a famous astronomer and a discoverer of many properties. And he was really the first person that we know of in history who speculated that E equals mc squared, that most famous equation in the universe, how that equation could be pertinent to the way that stars work. Prior to Eddington, people thought that stars worked by contraction, right? In the 18th century and 19th century, there had been a lot of work to discover the fact that when you compress a gas, it heats up, right? And the idea is that if stars formed from some kind of primordial gas, they were contracting, and this contraction would release heat. And Lord Kelvin, whose name was Thomson, not quite the same as me, but I don't know, I like the idea of having a superhero name along with a regular name, you know, he was Lord Kelvin, master of the universe. Came up with the idea that the contraction of balls of gas was the source of energy for stars, and he duly did his calculations and came up with an estimation that stars should live for a very long time, something on the order of about 10 million years. Well, Charles Darwin was active about the same time, and Charles Darwin looked at the geologic record that seemed to stretch back for billions of years, and he was not satisfied with his answer that the sun could only shine for a few million years. Sure, it's a long time, but it's not nearly long enough to be consistent with other evidence that's in nature. And that's one of the cool things about science, right? If you find something over here that seems to tell you something, like the sun can only live for 10 million years, and you find something over here that says the sun and the earth and living things must have been around for a couple of billion years at least, there's a discrepancy there highlighting that somebody is wrong. So science, among its more wonderful characteristics, is self-consistent, right? There's no such thing as a true paradox in nature. Nature either does something or it doesn't do something, right? So, you know, Lord Kelvin's approach to answering this question was very rigorous, very well justified, but it was very difficult for anybody to find any problem with it. Until Einstein came along and Arthur Eddington read this E equals mc squared insight and said, maybe inside of stars, matter is being converted into energy. Well, he didn't have any idea how, but it's a good thought, it's a good idea, and then they tried to figure out how. So, in about 1948, Einstein was active in about 1920 time frame, and Eddington. In about 1948, by that time they had discovered some nuclear energy stuff. Remember, this is after the atomic weapons and the Manhattan Project and whatnot. And scientists had come to understand processes of nuclear fusion and nuclear fission. Fusion is where you take two atoms and you stick them together, and fission is where a big atom will burp out some particles and become a different atomic species. And they discovered something about the energy required to make these things happen. So if you have an atomic nucleus and another atomic nucleus, they both are chock full of protons, and protons have a positive charge, and what you learn in elementary school is that like charges repel. So at first blush, if you're trying to get two atomic nuclei close together, they're going to say, no, no, I hate you, get away, you're too much like me, I want to find something different. I want to find an electron that's got a negative charge, right? So the protons inside the different atomic nuclei will push each other apart. So how is it possible that you could take two things chock full of protons and get them to stick together? What is it in nature that facilitates such an unholy union in terms of the electrical force? Well, interestingly enough, this is one of the things that really fascinates me about science at this era. By this time, I cannot find in the search of any literature of science anybody who said there was a magical, mystical, cosmological, cosmic force, some god, that says, you shall stick together, right? And holds atoms together against the will of the electrical force, right? Back in the days of Newton, when Newton was trying to figure out the gravitational force, when somebody asked him, what is gravity? What makes gravity? Newton said, oh, God did it. You know, it's God pulling everything together. It's the permeating spirit of the divine. And by the way, about 10% of Isaac Newton's writings were about alchemy. And other significant portion of his writings were about numerology and searching for the hidden code in the language, the mathematical code supposedly hidden in the language of the Bible. So Isaac Newton really straddled that gap between mysticism and science. But by the time the 1940s had rolled around and there was a need to talk about another force of nature that was stronger than the electrical force, nobody imagined, even for a moment, that it was magical. Instead, they went looking. They went looking for a new force of nature, different from gravity and electromagnetism, and they found it. The evidence of nature says that sometimes elements do stick together. But in order for that to happen, they've got to be moving really quickly. So, you know, people have a personal space, right? You don't want to get too close to somebody else, you know, who knows what kind of cooties they have. So we all have a personal space. We don't get too close to somebody. But if you're playing a sports game and you're running with a lot of energy, you might bump into somebody. You'll invade their personal space, right? The idea is that if you have more energy, specifically more energy of motion, then you can bang into something hard enough that you can overcome the electrical potential barrier that keeps you apart. And you get close enough and the strong, what's called the strong nuclear force, can grab hold and take these protons and these nuclei and bind them together against the pull of electrical forces. So, some scientists...
Is that God?
That's all right. So some scientists, this is a fellow named Ralph Alpher, this is Hans Bethe, and finally we have George Gamow. So it's an American, a German, and a Russian. And this is the 1940s, 1950s. This is, you know, the Cold War is really getting started. And we have these people from these various countries who decide to write a paper about the source of elements inside of stars. Now, like I said, you have to get moving very fast to stick together, to take one element and bind it with another in terms of its atomic nuclei. And these kinds of temperatures are much hotter than you could get in a blast furnace, right? We're talking millions of degrees. A blast furnace might get up to a couple thousand or a few thousand degrees. Where in nature can you have a temperature of millions of degrees? Well, they got back to this idea that Kelvin had with collapsing gases, gas clouds that made stars. And the notion there is that the center of these stars can heat up to millions of degrees. This is just basic thermodynamics. This is stuff that's been known about for 200 years. The center of stars gets really, really hot. Hot enough to make these nuclear reactions happen. So these folks, these three folks, Alpha, Beta, and Gamma, published a paper. Now, it was actually Ralph Alpher's PhD thesis, and his advisor, who had something to do with it, he wasn't just standing on the sidelines, was George Gamow. And Alpher wanted to publish this paper, and Gamow was supporting it, his name was on it, and it was Alpha and Gamma, or Alpher and Gamow. And Gamow is notorious for having one of the best senses of humor of any physicist who ever lived. And Gamow said, you know what, we've got an alpha and we've got a beta. No, we've got the gamma, we're missing a beta. Well, I happen to know Hans Bethe from Germany. And I know that Bethe has been working on this same kind of stuff about how the nuclear processes in stars work, so I'm just going to throw his name on the paper too. And he did. So it became known as the Alpha Beta Gamma, or the alphabet paper. So in 1948, they published the alphabet paper with a wink and a nudge from George Gamow. Gamow has written some wonderful physics books that explain stars and whatnot to a young reader and a non-specialist reader, and his books are still delightful, even 70 years after the fact. And anyway, they figured out that during the Big Bang, temperatures were hot enough, things were compact enough, that some nucleosynthesis would happen, and that something should be happening in stars. But there was this problem that whenever, it gets a bit technical, but I won't go into the details now, but whenever you try to get a nucleon, or a nucleus with 5 particles or 7 particles, nature says, there are no stable nuclei with 5 nucleons or 7 nucleons. I'm sorry?
7's perfect.
Yeah, well, I know. How about that? I never even thought about that. That's a good insight, Harry. 7's the perfect number, and nature said, no, not going to do it. Well, if you're trying to build elements by adding 1 proton at a time, shoving them in, hydrogen ion, hydrogen nuclei, 1 proton. You try to build the elements by adding 1 proton at a time. That works fine up until you get to beryllium. Hydrogen, helium, lithium. And beryllium, when you try to make beryllium by adding a proton to lithium, it quickly decays. It's radioactive. It doesn't stick together. It's like, no, I don't want to do this. I don't like this idea, right? So any kind of mechanism that these physicists try to figure out about how these it's called nucleosynthesis, there's your $5 word for the day, how cosmological nucleosynthesis happened, they always hit this barrier of either 5 or 7 particles, where nature and the energy measurements coming out of nuclear reactors and whatnot that told us at what energies these processes occur, they all said it just can't happen. There was a wall at 5 and 7. So they thought that, I don't know, maybe the Big Bang, maybe there was something that happened during the Big Bang, because stars obviously can't do it, because they can't get past 5 and 7. So maybe something in the Big Bang generated all of the elements. And this idea was scientific, but it happened to be incorrect. There were other attributes of the Big Bang that just didn't make sense. When you start looking for heavy elements as a product of the Big Bang. And instead, we found that almost all of the heavy elements that are common in nature are generated by processes within stars. Remember, 15 million degrees. And there's something called a triple alpha process, where you get 3 three of the nuclei from helium atoms, and if you happen to get three of them bumping into each other at once in a real kind of dog pile, then they will stick. Well, each helium nuclei has 2 protons and 2 neutrons. That's 4 particles. You meet them up with another 4 particles, and that can stick, but it tends to be unstable. But if you get 3 of them together, then you can start making carbon, right? Again, 2 protons in 3 different things. That's 2 times 3 is 6, and 6 is the number of protons in a carbon atom. So one of the first things that stars are able to produce outside of helium is carbon. And in fact, astronomers look out into the night sky and they can detect carbon stars, stars that are so suffused with carbon that they're almost like glowing coals, except they're powered by a nuclear fire. And the people who figured this out, who figured out that stars could generate all of these heavy elements, are the following. All right, the lady on the top and the gentleman right underneath her are a husband and wife team, Burbage. They're Margaret and Geoffrey Burbage. The person in the upper, what is your right? Upper right is William Fowler, and the person down in the lower corner is Fred Hoyle. Now, Fred Hoyle has lots of interesting stories about him. One of them is that he came up with the term Big Bang, and he did it as a criticism. It was meant as a derisive term, right? Well, you people think that the universe started in some kind of Big Bang? Oh, yes, precisely. No, that's not what I meant. And it stuck. The idea stuck. So Fred Hoyle came up with the notion of Big Bang. He believed instead that the evidence of nature pointed to something called the steady state universe, which I'm not going to talk about because it's not real. Fred Hoyle also really went to bat for somebody. One of the things that can happen to a star, which I'm not going to talk much about other than now, is that when a star dies, it can leave behind a kind of cinder of material that's essentially a gigantic atomic nucleus held together by gravity, and that's called a neutron star. And one of the people who was most important in discovering neutron stars is a lady by the name of Jocelyn Bell Brunel. And the other person who discovered neutron stars, whose name I forget, got a Nobel Prize. And Fred Hoyle went to bat for Jocelyn Burnell and said, what the heck is going on here? She did fantastic work, innovative work, one of the most important discoveries in astronomy in the past several years. Why isn't she getting the Nobel Prize? And the answer was, well, you know, she's a woman, which is baloney, malarkey, right? But he went to bat for her. And so when it came time to hand out Nobel Prizes for the discovery of the atomic processes inside of stars, guess who was passed over? Fred Hoyle, right? So politics sometimes makes its way into science, unfortunately. And there's a similar story about Einstein. Eventually they had to give Einstein a prize because he'd done so much. But they didn't want to give it to him for relativity because that was Jewish science. And I don't know, there's just something about that. So they gave him his Nobel Prize for figuring out the photoelectric effect, which is important. It has to do with solar panels and all that stuff. But the point is, prejudice is largely evident. Social prejudice can be evident even in some austere processes like the pursuit of science, and that's really unfortunate. These folks figured out how stars work, and their paper is called the B squared FH paper because it's Burbage, Fowler, and Hoyle. And it's a famous paper. It's about 100 pages long, and it is still one of the go-to papers for figuring out the nuclear energy plateaus and the way chemical elements are generated in the processes of stars. So how do we get from the Big Bang to stars? Well, after the Big Bang, there was hydrogen, helium, and a smattering of lithium. And that's pretty much it. Can you make a star from that? You betcha. Stars are almost always and almost exclusively big balls of hydrogen gas. Well, there was lots and lots and lots of hydrogen gas around. And these gas particles would conglomerate into clouds. Has to do with, if you trace it all the way back in time, it has to do with quantum uncertainties in the scale of the nugget that became our universe. This nugget started from a pinprick and became the universe, and when it was about pinprick size, quantum fluctuations were relevant, and it imprinted on the universe tiny little density variations, and these tiny density variations manifest subsequently about 380,000 years after the Big Bang. No, about 500,000 or so years after the Big Bang as clumpy little clouds. And these clumpy clouds would have gravity, right? The self-gravity, and the clouds would collapse in on themselves because of the gravity. And they would collapse enough that they would get hot, like Lord Kelvin figured out, and start producing nuclear energy and emitting light. These were the first stars in the universe. But they were all hydrogen. And one of the things about a purely hydrogen star is that it can grow to be very big. Astronomers have delineated between what they call population 1, population 2, and population 3 stars. So what do you think the first stars in the universe were called? Which population? 3. The first population are population 3 stars. Duh. Because our stars, right now, our stars are population 1 stars. They're the most important. Right? And if you go back in time and you look at stars that preceded the current generation of stars, you find population 2 stars. And somewhere back at the beginning of the universe, there were population 3 stars. Well, population 3 stars, there were no heavy elements around. Astronomers have this strange, peculiar tick of the language where they call any element heavier than helium a metal. So carbon and boron are metals in the lexicon of astronomers. So silicon, or I mean, everything that's not hydrogen and helium is a metal. So they can say, well, hydrogen and helium fusion in stars happens thusly, right? And that's most of the time what's most relevant. Oh, and then you get the metals. Well, back in the early universe, there were no metals, even though lithium's a metal, chemically, right? Anyway, so there were essentially no metals. And one of the things that metals do, if metals are available in the population 2 and population 1 stars, when stars are formed from those eras of the universe, there's going to be a little bit of metal around. There's going to be some carbon, some oxygen, some nitrogen, and whatnot. And those elements inside of a gas cloud, when it's forming a star, tend to put a pretty low upper limit on how big the star can be. Because those metal, I'm going to describe it prosaically, it's not quite how it happens, but the metals get heated up, and because they're heated up inside the star, they cause more radiation outflow, and the radiation outflow of a forming star is hot enough to blow out the outer layers of the star. It just can't grow any bigger. It's getting too hot, too big for itself. But that didn't happen in the early universe. In the early universe, you had essentially hydrogen and helium, and those stars could get to be 200, 300 times the mass of the sun. Gigantic stars, brilliant blue stars. But one of the truisms of nature is the bigger you are, the quicker you fall. And so these giant, massive blue stars only stuck around for a few million years before they exploded. But when they exploded, suddenly they were these delightful bags of metal. There was carbon and nitrogen and oxygen. Again, this is astronomical metals, not chemical metals. There were all these wonderful elements that came about just a few million years after the Big Bang, and they populated all of space, so that subsequent generation 2 stars and generation 1 stars, which is subsequent, would incorporate these metals. And these gas clouds weren't just star size. Some of the gas clouds from which stars formed were gigantic. And they enabled the formation of the first dwarf galaxies. So, for example, this is kind of a dwarf galaxy hanging out over here, and it's making nicey nice with this giant barred spiral galaxy. This, in my opinion, this is one of the most beautiful galaxies in the night sky. But it's hard to pick one because there are billions of them, perhaps trillions of these things. So picking one exemplar as the most beautiful galaxy is hard. But I really like this one, and it's interacting. And it's hard to see on this screen, but you see this little arm right here, this really hazy little bit? Well, that is a little bit of the large galaxy that's being pulled towards a smaller galaxy. So galaxies interact and collide sometimes. And when galaxies collide, the universe just, it's over. No, I'm kidding. No, actually, when galaxies collide, what you see is not much interesting, because galaxies are mostly empty space. So the stars from one galaxy can whiz by the stars of another galaxy, and they might do a little gravitational dance, but they're not going to smash into each other. Right? So when galaxies collide, it's not a particularly violent thing, but it is a very creative thing. And the first galaxies in the universe were likely very small galaxies, and they congealed and collided. And when you collide a galaxy, the stars are fine, but the gas clouds that are in a galaxy suddenly have a lot more material to work with. And so the gas clouds form a lot of new stars. So anytime you see galaxies colliding, you'll see bright blue newborn stars. And you know, if you look at this galaxy, you see this ring of blue stars out here because some gas is likely streaming from this galaxy onto this one. And over millions or billions of years, it's creating a starburst event. So that's one of the ways that you get new stars, even in today's universe, is you get colliding gas clouds. This is another one of my picks for the most beautiful galaxy observable from Earth. This is called the Sombrero Galaxy, which is kind of like a hat. I'm thinking about making a hat like that. That'd be kind of cool. This is a galaxy that's similar to the Milky Way galaxy, except from our perspective on Earth, as we see this thing, we're seeing it edge on. So we see all the gas and dust in the disk, and then the halo of stars around it. This glow, this nebulous glow, in fact, these were called nebula, a word, that's a Greek for cloud. Anyway, this nebulous glow around the galaxy is actually comprised of billions of individual stars. That's not glowing gas, it's stars. There are a tremendous, titanic number, an unimaginable, inconceivable number of stars in that universe. But you can write down an equation that tells you how many there are, but it's just mind-numbing to think about. To the point where they took the Hubble telescope and they pointed it at a patch of sky that's smaller, much smaller than a postage stamp. And they had the Hubble telescope stare at this blank patch of sky. There was nothing interesting in this patch of sky. Nobody had ever found anything interesting. It was just, there's no star, there's no nebula, there's just nothing. And so they wanted the Hubble telescope to validate that there was in fact nothing there. So they parked the Hubble telescope in orbit around the Earth, and over a period of years, they exposed this picture. I forget, Joanne or anybody, you know, that it's something like 30 days worth of exposure, right? It just kept staring at this blank spot in the sky. Imagine being an astronomer trying to do that. Thank gosh for computers, right? I still don't see anything. You know, 30 days worth of staring at the same point in the sky. And when they developed the image that came out of all of that light capturing time, they found that this blank spot in the sky was festooned with galaxies. Right? It's called the Hubble Ultra Deep Field. Each one of the dots each one of the smears, each one of those dots is a whole other island universe. So there are trillions of stars in the universe, and there are all these, as you might say, alchemical factories transmuting one element into another. So the alchemists have many opportunities in the universe to take advantage of chemical alchemy. They're really hard to get to. The Philosopher's Stone, maybe we should call it instead the Philosopher's Star.
22 days.
22 days, thank you.
I just see September 24th, 2003 through January 16th, 2004. The telescope data was accumulated over a period of, that's almost 4 months.
Well, it wasn't.
Days, but the actual exposure time.
It was looking at other things during that calendar period, but the exposure time, 22 days worth of light gathering. All right, a barred spiral. This is the best picture I could find of a galaxy that probably looks the most like what our Milky Way galaxy looks like. It's called a barred spiral. Anybody know why? It's got a bar in it. And they validated that the Milky Way galaxy has a bar. And where are we? Where do we fit in the universe? Are we at the center of the universe in some gigantic galaxy? Are we at the center of that galaxy? Does the universe revolve around us? No. We're in a pretty boring, medium-sized galaxy that doesn't, I mean, if I had to pick the most beautiful galaxies in the sky, this one probably wouldn't make the list. I mean, it's nice. Yeah, those galaxies go. And it's all right. And where are we? We're somewhere like right around here. We're not even close to the action, right? We're just a I'm
Are
sorry.
those arms going in? Is that collapsing as we look at it? I mean, it's like I'd be stabbing them out, but is that, it implies that there's some kind of motion to that.
Yeah, there is a motion to that. So the question is this galaxy collapsing? Is it like water going down a drain?
Right, exactly.
All the arms gonna pull in? And the short answer to that is no. And that's one of the reasons that scientists determine that dark matter exists, is because one of the things that dark matter can do is essentially keep these kinds of galaxies puffed out. It's a halo of dark matter. I won't go into much more detail about that. But yeah, so these things whirl and pinwheel through space. It takes, 200 million years for our sun to make an orbit around our galaxy. So there's a galactic year as well as a solar year. Yeah, we're somewhere around there. There's one spiral arm, in our galaxy, there's one spiral arm more distant than the spiral arm we're in. So I guess there's a really faint arm here. We're in the, what's it called, the Orion spiral arm, I think. We have to give names to everything, right? One of the things I mentioned about science is that one of the first things science ever does is stamp collecting, right? It says, what is this thing? Can I give it a name, and what distinguishes it from this other thing? Why is a star different than a sand grain? You know, why is a dog different than a fish, etc. So figuring out what separates one thing from another and then coming up with a framework to explain those differences is one of the big things that science does. So here's a picture of a big, speaking of the Orion spiral arm, this is a picture of the constellation Orion. This is Betelgeuse, Rigel, some other bright stars in here. And this is Orion's belt and the sword of Orion, and there's a beautiful gas cloud there. But the whole thing is just embedded in this gigantic gas cloud, forming new stars all the time. Betelgeuse, by the way, have you heard the story, the news about Betelgeuse? Betelgeuse is dimming. And stars have lives. I alluded to that earlier when I said that the first stars in the universe only lived for a few million years. Stars have lifetimes. And the bigger you are, the shorter your lifetime. And Betelgeuse is a big, heavy star, and it's approaching the end of its life. And one of the things stars do is that they generate these nuclear elements through the alchemy of fusion. And then that particular element that's powering the nuclear fusion is depleted, and the star goes, and it starts contracting. Well, as it contracts, like Lord Kelvin told us, As it contracts, it gets hotter. Well, it might get hot enough to burn some other element, right? So instead of fusing helium into carbon, now it fuses carbon into silicon, right? So if a star is hot enough, if it's big enough, it can get hot enough to fuse all kinds of elements, up until you reach iron, exactly. So once you get to iron in a star, the star turns off. And that can happen in a matter of seconds. A star that has been persisting in our night sky for millions or billions of years can turn off in a matter of seconds. And when the energy generation in the core stops, gravity says, I win, and takes the star and smashes it down onto this iron core. And when it hits this highly compressed iron core, there's a shock wave that reverberates throughout the body of the star and tears it apart, just shreds the thing in an explosion that emits more light than all the stars in our galaxy combined. Anyway, I'm getting ahead of myself. Isn't it exciting? So here's the Orion Nebula down here, right? You maybe have seen pictures of the Orion Nebula. The Orion Nebula is just one small congealment of gas inside of a gigantic gas cloud. And the first stars were blue and hot, and they formed about 200 million years or so after the Big Bang, maybe a little more than that. They were large and luminous, they were short-lived, and they were mostly gone. The first generation, population 3 stars, were mostly gone after a billion years. And they produced a lot of these metals that I talked about. I talked about the supergiant star. Where does our star fit in? Our star is called a yellow dwarf star. Not only is our galaxy not spectacular, not only is our location not spectacular, even our star is boring. Which is good. You want a boring star for evolution to happen, for life to arise on a planet. But there's a star that's even more boring than ours. It's called a K-type dwarf star. And K-dwarfs persist for about twice as long as G-type stars. And K-dwarfs may be an even more ideal place to find evolved life in the galaxy. And then there's an even cooler star, but this thing, like a lot of, well, it's kind of got a Napoleon complex. These little M-type dwarf stars are very rambunctious. They're always spitting off flares and particles and X-rays and whatnot, so it's probably not a good place for life. But these K-type stars probably are. All right. Sometimes stars blow up. I told you about that. Right? This is an artist's embellishment of an actual picture of an X-ray picture of the Crab Nebula. The Crab Nebula is in the constellation Taurus, the Bull, and it is the remnant of an exploded star. And when these heavy stars explode, remember the first stars, generation 3, made carbon and oxygen and nitrogen. But on Earth, we've got things like iron and silicon. Where did all that come from? It came from population 2 stars. Now, 2 being in the middle, it's easy to remember, right? Population 2 stars generated things like splattering iron and nickel and magnesium and other heavier elements throughout space. And I'll give you more details about that in a moment. And then occasionally, the remnant of a star, the hard core that's left over after the star explodes, like these neutron stars in this depiction from NASA, neutron stars might get close enough to each other that they collide. And when a neutron star collides, you get even heavier elements. You get things like gold and platinum. Well, that's one of the reasons that those elements are so rare in the universe and on Earth, is because colliding neutron stars don't happen every Thursday. Right? So here's how I'm going to end today, and we'll continue next time. This is a beautiful chart if you're interested in astrophysics. This is the chemical periodic table of the elements, embellished with information about the origin of particular elements. So from this chart, you can tell whether or not an element was generated during the Big Bang, or whether it's been generated in low-mass stars, or in neutron star collisions, etc. All right, I'll take a couple minutes for questions, and then we'll wrap up. Yeah?
I just want to know how to search for that to find that chart.
On Wikipedia, you can find, I don't know, how would you find cosmological origin of the elements? It's pretty easy to, yeah, if you just do anything like the cosmological element source, cosmological periodic table, anything like that, you'll find it. There's a whole article on it on Wikipedia. Other questions? Yeah.
The newly made element, the newly made elements, the ones that come from like gold from your emerging neutron stars, when they're hot and fresh, are they kind of radioactive? I know from nuclear reactors there's common elements, but they give off a lot of radioactivity. Like
Yes.
solar.
Yeah, a lot of the, so the question is, do some of those heavy elements, when they're created by supernovas or colliding neutron stars, are those elements radioactive? Absolutely. In fact, a lot of the light and energy that we receive on Earth from these events is energy of fission radiation. And then after, anywhere from a few minutes to a few thousand years to a few million years, these elements have decayed through fission because they're unstable. That's where the radiation comes from. And they become fairly benign. But yes, highly radioactive events. You don't want to be there.
They're saying that Betelgeuse could collapse in momentarily or 10,000 years.
Yeah, it's and likely Betelgeuse has gone through a change of life. It's no longer generating possibly carbon at its core. Maybe it's gone on to silicon burning, which results in iron. That can persist for a number of years. If we're wrong about, if I'm wrong about that, I don't know, I haven't read about it. But if instead it's later in its life cycle and burning some other element, each phase of its life gets shorter and shorter and shorter. So it could be imminent. It could, well, in cosmological terms, it's definitely imminent. But is it going to be 10,000 years or 10 days before Betelgeuse explodes? My bet's on the later time because it's got some material work to it.
This is fascinating. It's quadrupled or more of my understanding of this whole process. But the thing that's hardest to get my mind around is this Big Bang where you start with a pinhead and wind up with trillions of stars. Is there any way to possibly try to understand that?
Were you here for my prior two lectures? Okay. Yes. The answer is yes. There is a way to understand that. I've got my lectures, my prior two talks up on YouTube.
They're on YouTube. You can look on YouTube and see the lectures.
Good.
When two galaxies collide, Scott, are there any conjectures or any thoughts about anything interesting about dark matter colliding in that time? Would it have anything to do with anything?
Yeah. So what I know for certain, I'm speculative about specific galaxies, but what I know for certain is that galaxies often cluster into larger agglomerations called galactic clusters. Right? We're part of the Coma cluster. Anyway, yeah, certainly the local group, but we're also part of a giant cluster. And when you get clusters of galaxy with their attendant dark matter colliding and rushing through each other, there's at least one instance where the dark matter went, "See y'all later," and kept going. And the galaxies congealed into a tighter gravitational orbit around each other. But the dark matter is off somewhere else in space. And how do we know that? Because dark matter doesn't, no way, no how, emit any light. No X-rays, no ultraviolet rays, no infrared light, no light whatsoever. That's why it's called dark matter. Well, remember the Eddington experiment with the starlight grazing the sun? Astronomers have looked at this patch in space where this galactic cluster collided and found that the paths of distant stars has been warped by a presence of matter that we can't see, we can't detect. But gravity tells us it's there. So yes, there are cases where the dark matter can just keep on going. And it probably happens with galaxies too, but it may be that there's not enough for them to have detected gravitational warping anomalies from that. But I could be wrong. But yes, it certainly happens. All right.
I guess I was assuming that the formation of the chemicals of the different elements was this kind of binary, step-by-step process that each one, but I thought a few of the things you said seemed to imply that that's not as binary as
Right.
I implied.
Yeah, so some of the elements are formed in groups. There's a thing called the CNO cycle in stars. Carbon, nitrogen, and oxygen are generally formed at the same time through a process that overcomes that 5 and 8 nucleon barrier. And it gets the nuclear physics gets a little complicated, but there are groups of elements that are formed at the same time because they have very similar nuclear binding energies. Right. All right. Yeah.
What is the form of matter? I guess, it's not something that.
Solid, liquid? Is that what you're talking about? Is it solid, liquid, gas? Yeah, most of the matter in the universe is plasma. So it's so hot that the electrons have been stripped off of the atoms, and it's just a plasma soup. The electrons are flitting around independent of the atomic nuclei. And I say most of the matter in the universe is that because most of the matter in the universe is in stars. Well, I don't know, maybe there's more in gas, but a lot of the gas is ionized too because there's stars embedded within it. But most of the matter is somewhere in a dividing line between plasma, like a flame, and gas. And it's only a thin patina of matter on this giant ball of gas that is solid crusty bits like we get to make the planets. All right, I got to wrap up. The church service is starting, but we'll continue this discussion next month. Thank you very much.